let's explore the second type of asymptotic notation, which is known as big omega notation. In the context of computer science and programming, omega notation is a crucial tool used to analyze the performance of an algorithm, particularly in terms of their time and space complexity. It describes the lower bound of an algorithm growth rate, helping us to understand how the algorithm behaves as the input size increases. Formally, we say that a function f of n is big omega of g of n if there exists a positive constancy in n sub 0 such that f of n is greater than or equal to some constant c multiplied by g of n for all n greater than or equal to n sub 0. Let's break this definition down. F of n represents the runtime or space requirement of an algorithm we are analyzing. G of n is a comparison factor that establishes a lower bound, often chosen to represent a simple function like linear time or logarithmic time. C is a positive constant that scales the comparison factor, ensuring that G of n accurately reflects a lower limit of f of n. N sub 0 is a threshold value beyond which the inequality holds true, meaning that for all input size n greater than or equal to n sub 0, f of n will consistently perform at least as well as some constant c times g of n. In practical terms, omega notation indicates that for sufficiently large input size, the algorithm performance will not drop below certain level represented by g of n. This is particularly valuable for understanding the best case scenario of an algorithm's efficiency, providing a guarantee on its minimum performance. Now, let's look at some examples that illustrate omega notation in action. Consider the function f of n equal to 3n cubed plus n squared plus n plus 20. At first glance, this function may seem complex, but focusing on its growth reveals the key insights. As n increases, the term 3n cubed becomes the dominant factor, overshadowing the other terms. In this context, we can confidently express f of n equal to big omega of n cubed. This notation indicates that for sufficiently larger value of n, the function f of n will not grow at least as fast as n cubed, multiplied by some positive constant. Essentially, no matter how large n becomes, f of n will not fall below this cubic growth. This understanding is crucial for evaluating the minimum time or space required by an algorithm. Now, let's examine another function, f of n equal to 3 to the power of n plus 2. Here, we encounter an exponential function. The term 3 to the power of n quickly emerges as the powerhouse of this equation. As n increases, 3 to the power of n grows at faster rate, leaving the constant 2 far behind. In this scenario, we express our finding as f of n equal to big omega of 3 to the power of n. This notation reveals that for larger value of n, the function f of n will grow at least as fast as 3 to the power of n. This insight ensures that the algorithm will not perform worse than this exponential growth rate, highlighting the rapid resource consumption that can occur. Finally, let's consider a function that showcases logarithmic growth. F of n equal to n log n plus 5. In this case, the term n log n dominates the behavior of f of n as n increases. While plus 5 is a constant, it becomes insignificant compared to the logarithmic term. We can express this relationship as f of n equal to big omega of n log n. This indicates that for sufficiently large value of n, the function f of n grows at least as fast as n log n. This understanding is vital, especially in the context like sorting algorithms, where knowing that an algorithm won't perform worse than this growth rate can inform our choices in algorithm design. Next, let's look at the different lower bound for the function f of n equal to 3n cubed plus n squared plus n plus 20. Here, the dominant term is 3n cubed, so we can express its growth rate as f of n equal to big omega of n cubed. Because f of n is greater than or equal to 3n cubed, this indicates that f of n grows at least as fast as n cubed, making it a closest and most accurate lower bound. Then, we transition to the next valid lower bound, a quadratic lower bound. We can express f of n equal to big omega of n squared. Since 3n cube grows faster than n squared, we can express f of n is greater than or equal to 3n squared. This shows that f of n also grows at least as fast as n squared. Afterwards, we consider the linear bound. F of n equal to big omega of n. The leading term is 3n cubed, clearly surpass n for larger value of n. Thus, f of n greater than or equal to n. This confirms that f of n grows at least as fast as n. Finally, we can analyze the constant lower bound. F of n equal to big O of 1. Since f of n remains above 20 for any n greater than or equal to 1, it follows that f of n is greater than or equal to 20. This indicates that f of n is bounded below by a constant. In conclusion, we have established the following lower bounds for the function f of n equal to big omega of n cubed, f of n equal to big omega of n squared, f of n equal to big omega of n, and f of n equal to big omega of constant time. This analysis shows that while n(q) is the closest lower bound, n squared, n and a constant are also a valid lower bound for the function f of n. Finally, let's analyze the lower bound for function f of n equal to 2 power n step by step, focusing on the exponential nature of this function. First, let's identify the function we are analyzing, f of n equal to 2 power n. Next, we determine the recommended lower bound starting with the exponential lower bound. The function f of n is equal to 2 power n, so clearly f of n equal to big omega of to the power of n. This indicates that f of n is bounded below by itself, making it the closest and most accurate lower bound. Then, we consider the polynomial lower bound, f of n equal to big omega of n power k. For any k, to the power of n grows faster than any polynomial in the power of k as n increases. Thus, f of n equal to big omega of n the power of k. This shows that f of n grows at least as fast as any polynomial function. Afterwards, we analyze the linear bound, f of n equal to big omega of n. Since to the power of n grows much faster than n for large value of n, we can express f of n equal to big omega of n. This confirms that f of n grows at least as fast as n. Finally, we look at a constant lower bound, f of n equal to big omega of 1. Since f of n is greater than 0 for all n greater than or equal to 0, we have f of n equal to big omega of 1. This indicates that f of n is also bounded below by a constant. In conclusion, we have established the following lower bounds for the function. F of n equal to big omega of to the power of n, which is the most accurate representation, and the other valid representations are f of n equal to big omega of n power k, f of n equal to big omega of n, and f of n equal to big omega of constant. This analysis shows that while to the power of n is the closest lower bound, it is also bounded by a polynomial, linear, and a constant function, all of which are valid lower bound for f of n. To conclude, let's delve into a complex hierarchy with f of n equal to n squared as our focal point. We can clearly illustrate the relationship among upper bound, lower bound, and tight bounds within this hierarchy. All the classes of time function that reside on the left side serve as lower bound, which include several classes of function that grows slower than n squared. This function serves as benchmark for minimum growth rate of n squared. Conversely, all the classes that reside on the right-hand side serve as an upper bound. Here we see that not only does n squared fit within this category, but it also serves as an upper bound for various faster growing functions. Importantly, n squared itself acts as tight bound, accurately representing its growth rate. This means n squared effectively captures the complexity of itself, providing the most precise characterization of its performance. While n squared serves as both upper and lower bound within this hierarchy, it is most accurately defined as its own tight bound. So, we can represent this as f of n equal to theta of n squared, because f of n is both big O of n squared and big omega of n squared, which serves as the upper and lower bound, and we call it as the tight bound of itself.